Our next topic is all about looking at each individual element, its isotopes, and its average atomic mass, and how do we get those, and how are they different? So let's get started. So remember, we've already talked a little bit about the atomic structure. We have 3 subatomic particles, okay? And those subatomic particles are protons, neutrons, and electrons. So remember, protons and neutrons, right, are located in the nucleus, and the electrons are located in the it's most likely that you're going to find an electron, right? So the smallest piece of matter we know are these atoms. And now we're going to look at the orientation and the numbers of protons and neutrons and electrons and how it applies to average atomic mass and isotopes. So isotopes have a different number of neutrons but the same number of protons. So you can see in the picture here, we're changing the number of neutrons starting with the smallest isotope and getting larger. So the one thing I do want to throw in here is to kind of explain what this representation on the bottom here, what this all means. So if we look and we use H1 as our example, so remember H is the atomic symbol, and the atomic symbol is the either single uppercase letter or the uppercase and a lowercase letter that represents each element. Then this 1 represents the mass number. Of whichever isotope we're talking about. So right now we're using this first one in the green as our example. And then in the blank spot on the bottom, normally you would find the atomic number. So if we fill in for H, the atomic number is 1. So we could fill that in there too. So I just want you to understand this representation and don't be shocked if you see some problems with it given this way instead of written out completely. The most important thing about isotopes is that they're still the same element. Remember, they're classified by atomic number, which is your number of protons. Okay, so atomic number of protons, not our number of neutrons. Okay, our number of neutrons is only going to affect atomic mass. So it's not going to change what element we're talking about. It's just going to change its mass. A great way to define isotopes or think about isotopes is comparing it to kind of like breeds of dogs, okay? A dog is a dog, but there's multiple different types of dogs. So you see here we have a bunch of different pictures. So we have a pug, we have a husky, we have a golden, and we have a puppy that I'm not 100% sure what the breed is. But isotopes are pretty much the same type of thing. They're the same element, but because we change its number of neutrons, it's going to be a little bit different and it's going to have a different mass. But it's still the same thing. It's still classified as the same type of atom, the same type of element. So we've talked before about the difference between mass number and atomic mass. Remember, atomic mass is the number given as a decimal. Mass number is rounded to a whole number. So isotopes have different mass numbers because of our number of neutrons. Because remember, mass number equals our number of neutrons plus our number of protons, because those contain the majority of the mass of an atom. And you can see that in the picture, our number of neutrons increases as our mass number increases. So they have a positive correlation or a positive relationship between the mass number and its isotope and the mass number and its number of neutrons. So here we have one example. It's an isotope and the subatomic particles. So we're given the three isotopes of Si. Remember, Si is silicon, number 14. And we know because it's number 14, its atomic number is number 14, we know its number of protons for each one of these isotopes are all going to be the same. So we also know my number of protons and my number of electrons are going to be the same because of atomic number. So we can also fill in my number of electrons as being 14. So the only thing that's going to change now is my number of neutrons. So to establish my number of neutrons, remember we're going to do mass number minus atomic number. So we have my mass number for each one of these, 28, 29, and 30. And because we've filled out protons and electrons already, we know that my atomic number is 14. So for the first one, 28 minus 14 gives us 14 again. And since the other two just go up by 1, we can fill in its number of neutrons as 15 and 16. So remember, each one of these isotopes is still the same type of atom. It's still silicon, but it has a different atomic mass or a different number of a different number of neutrons. You might be wondering, why does this matter? Why are isotopes important? Now, what does it really matter to our day-to-day lives? Well, isotopes are actually what are used for carbon dating. So when we date fossils or relics, we actually look at using an isotope called C14 or carbon 14. Because as time goes on, the levels of carbon 14 in a substance and in the air change. So when a person or a animal dies, its level of carbon 14 is no longer staying standard and it starts to decay at a specific rate. So later on in the year, when we start talking about nuclear chem and radioactivity, we'll talk more about this. So the other side of isotopes is looking at the average atomic mass. Atomic mass on the periodic table is actually given as a decimal because it's an average of all that's elements isotopes. So we saw before that hydrogen has 3 specific isotopes, okay? Atomic mass of 1, 2, and 3. So the average atomic mass that's given on the periodic table is actually an average of all 3 of those. And we're going to talk about how to calculate that by knowing what the isotopes are and how much they are found in the real world or in nature. For us to calculate average atomic mass, there are 2 numbers that we need to know. We need to know the isotope and we need to know its abundance. So for the isotope, what we mean is that we need to know its mass number. Okay, and abundance is the percentage out of 100 that isotope happens. Okay, that isotope is present. So what we're going to do is we're going to multiply those, okay, and that's what we mean by times. So we're going to multiply, and then once we get that answer, we're going to add them together. And that will give us our overall average atomic mass. And remember, average atomic mass has of AMU. So the last thing we're going to do is we're going to look at an example problem. We are going to go over this during class, but I just wanted to walk you through how to set up one problem so that you've at least seen it before you come to class. So we have 3 isotopes of iodine, 127 at 80% abundance, 126 at 17% abundance, and 128 at 3% abundance. So remember, abundance in percentages should always end up equaling 100%. But when we do math, we don't want to multiply by a percent, so we're going to change that percent into a decimal. So that means the first thing we're going to get is we're going to get 127 times 0.8, and then we're going to get that plus 126 times 0.17 plus 128. And because that's only 3%, you get 0.3. And that sets up the first part of our problem. So this is going to equal my next step, which I'm going to do my multiplication first. So I'm going to get 101.6 plus 21.42 plus 3.84. And then now that I've done that multiplication, I'm just going to add my 3 numbers up. And that's going to give me a total of 126.86. And we're going to add our unit AMU. So this number should represent or should be pretty close to the average atomic mass that you get off of the periodic table. So this is how we do a problem. We're going to practice these in class. I have a PhET simulation you guys are going to work on that will help you understand this stuff a little bit. And I'm always available for questions. So let this sink in a little bit, and I will see you guys in class.